Hello everyone and welcome back to your YouTube channel and welcome to this amazing video today. As you must be aware, I am recording this series of videos related with electromechanical conversion systems. And one very important aspect is the DC machines. So as I explained during classes, during the theoretical part, I already said that the DC machine has a lot of applications in the past. The DC machine, specifically the DC motor, was quite interesting for variable speed applications. So as a motor in many industrial applications where the rotational speed must change and also the direction, the DC motor offers several advantages for that application. However, in recent time, power electronics drive, the cost of the power electronic drive has decreased so much. So that allowed the induction machines to take over. The combination of electronic devices like the drive, power drive, together with the induction motor, take over the main application for variable rotational speed in the industrial system. Also, the DC generator. The DC generator was used at the very beginning of the power utilities, especially during the famous direct current AC current war. During the war of currents in the past, between Nikola Tesla and Thomas Alva Edison, the DC machine was a fundamental element for producing DC current. However, during the time, we realized that the DC generators, they have a relative high cost of maintenance, so the DC machine started to fade over the time. So probably you are wondering why, if the DC machine has not so many applications in the modern world, I am teaching about direct current machines. And the reason is that pedagogically, from the education point of view, is simple to understand the concepts of rotating machine, starting with the direct current machines. So today I have extremely simple example, but don't disregard the importance of this exercise, because in this example, the numerical example is extremely straightforward. But the thing is that I want that all my students to understand the circuit model for the DC shunt generator. So without further delay, let's start this explanation about the DC generator that we are discussing today. A shunt DC generator, and this is very important because it's telling you the topology of the generator. This is a self-excited DC shunt generator and is directly connected to a resistor 50 ohms load and the current of 10 amps flow. If the armature resistance is 1 ohms, determine the terminal voltage and the AMF. In this case, for the solution, something that is very important that we need to add over here is neglect the field winding. So again, the important part over here in this exercise is that you understand the circuit model of the DC machine. So if you look over here, this is the circuit model for the DC shunt generator. So why do we use the name DC shunt generator? Well, in the circuit model, you can see that this is the field winding. And the field winding is connected in parallel or shunt connection to the armature. So it's clear because you can see the labels F1 and F2 to define the field winding, and they are directly parallel connected to the armature And you can see over here the armature has the labels A1 and A2. So this is a shunt generator because when we establish a voltage here at the armature, that voltage is used to create the field winding, the current moving on the field winding, creating that. So the armature circuit is quite interesting because we have an ideal voltage source representing the electromechanical conversion. We have mechanical power applied to the shaft, and we are producing here inducing here the MMF. This is the armature voltage. However, the armature has some copper windings, copper wires, and there is a series resistance representing the copper, the resistance on that copper. So as you can see, the direction of the armature current is going out because this is again a generator. When the current arrives here to this node, the current is divided in two. One current is going to the load and one current that is going across the field winding. The reality is that the field winding is created using a very thin copper or very small cross-section of wires. So the resistance, it tends to be a bit higher. So for instance, in this problem, we are assuming that this current is zero. So the armature current is equal to the terminal current. And in this, that is this very specific case. So let's start with the solution. And to be honest, the first step is very simple. Because if we know the terminal voltage is the same voltage applied to the load, to the terminal of the load. And the resistance is here, this resistance 50 ohms. If the current is 10 amps, we apply just the very simple Ohm's law. And Ohm's law say terminal voltage is load current multiplied by the resistor current. So here we multiply 50 ohms by 10 amps and we obtain the beautiful 500 ohms and 500 volts, and that is the voltage across the terminals. Now the second question here is to obtain the armature current. But the armature current, we can use the Kirchhoff voltage law because we know here the terminal voltage. So what we need to do is basically use the Kirchhoff voltage law through this loop. And it is extremely simple. Using Kirchhoff voltage law, remember, we can say that the terminal voltage is the armature voltage minus the voltage drop across the armature winding. So reordaining or rewriting the equation, the armature voltage will be the voltage across the terminal plus the voltage drop across the resistor at the stator, at the armature, sorry. The very important thing is that you must remember that in the circuit, armature current is equal to the field current plus the terminal current. But for this very specific example, we know that we can neglect the field current. So neglecting the field current made the armature current equal to the terminal current. So here we can use again the 10 amps and 10 amps multiplied by 1 ohms plus 500. We obtain the voltage across the armature. So what is important over here is that we have a voltage drop across the armature, the resistance across the armature, the copper on the wires of the armature of 10 volts. So always if we are working with a DC generator, shunt DC generator, the voltage at the armature should be larger than the terminal voltage. In other words, always when we are working with a DC shunt generator, This voltage, that is the induced voltage, should be larger than the terminal voltage. So we reached the very end of this exercise. I know that this exercise was basically applying circuit analysis. All my students, they are extremely clever and they have a very important understanding of circuit analysis. However, the important part is that you clearly understand the different components of the circuit model. And in this video, I show you the circuit model and a brief explanation of the different currents and voltages of the DC shunt generator. So this is the very end of this video. I hope that you find the explanation useful for your studies. I hope you enjoyed the explanation and you learn how to analyze the circuit model of the DC shunt generators. And if you like this video, please drop a comment or make any question and I will be extremely happy to support you. So this is all for this video. Thank you very much for watching and I will see you at the next one. Bye now.